Okay, so in this video, we're simply going to talk about carbohydrates. And to begin with, we say these are one of the most abundant type of organic molecules that we ever find. Now, we're coming from a background where you learned atomic theory and chemical bonding. So all the knowledge that you have from the first two topics, for those that are taking Bio 1400, the Wunza one, you are just being prepared to be able to identify the type of bonds that are found in these biomolecules. Yeah, so the first molecule that you observed was water, which is mostly going to be a suitable solvent for all, if not some, of these biomolecules that we'll be discussing. And to start the breakdown of these biomolecules, the first one that we look at are simply sugars, or also known as carbohydrates. So these have an empirical formula that consists of a ratio of 1 to 2 to 1. So we say we have carbon, we have hydrogen, then we have oxygen. So this is said to be the empirical formula of all carbohydrates, provided the N is always going to be greater than or equal to 3. Yeah, so the least number of carbon atoms, or the least carbon chain you ever see, or the smallest simple sugar that you can easily observe, is simply one that consists of 3 carbon atoms. So the least number N can have is 3. A perfect illustration of why this is our empirical formula is glucose. This is the common sugar that people are aware of. So this guy here is the actual formula for glucose, but there's a number that can divide this, which is just what? Which is just 6. So no wonder this can be, or could have been written like this. Yeah, so this is the main reason why we say the carbon hydrogen to oxygen ratio is always going to be a 1:1. And the main importance of these carbohydrates is that they help us in terms of providing or being the source of energy in our diet, and also act as storage form in terms of energy. So not only is it an instant energy giving biomolecule, but sometimes it can also exist as a form of storage. Yeah, so here we have a perfect illustration, which is glycogen, which is stored in the liver. And not only are they needed for energy, but these are also going to be offering some structural support in cell membranes. Yeah, so here we are simply saying the cell membrane components such as proteins, carbohydrates, and phospholipids. So all these biomolecules make up certain components or certain parts of cells. Yeah, so this is the overall picture of what carbohydrates are. Now, then the name, these are also known sugars. The name sugars came about because of their physical sweet taste. That's the main reason why this came about. Yeah, so most, or if not all, carbohydrates have a sweet taste. That being said, we can now look at the type of carbohydrates that we're going to dwell on. So these are the main type of carbohydrates that we're going to discuss. These are called the classes of carbohydrates. Now, before we even talk about these classes of carbohydrates, the other thing, just for your own information that you should know, you probably won't be assessed, but you should know to say the need of mammals or humans in particular to have a sufficient or a steady supply of carbohydrates in their diet is because of some of the disorders that people have, either by having a lot of carbohydrates or having a limit to the intake that they have. So if someone is not taking as much carbohydrates as their body needs, these are some of the conditions that people have. You probably have heard of people having diabetes, right? The common ones is people having diabetes and being lactose intolerance. So these are just, for your own information, things that you can take note of. Yeah, so these are the diseases that people are often exposed to whenever they have an unsteady or unstable supply of carbohydrates. So sometimes, though people mistakenly think that people who have commonly this, no wonder you call this what some people say, what, sugar disease, right? You've heard people mentioning that. So this is doesn't entirely mean that the people or rather abuses the intake of sugar. Sometimes could be a low supply of sugar to their system, like they've been taking less amount of sugar over a certain period of time. So it could either be both ways. Yeah, so then you have galactosemia, which is just a build-up of galactose in the blood. So it causes undigested sugars to build up over a certain period of time. Yeah, the same applies to glycogen storage diseases, the results of defects in the processing of glycogen synthesis. So glycogen is mostly needed. So for those that are athletes, there's always a certain limit to how much they can take in terms of sugar, or rather carbohydrates containing foods before they perform. Why? Because the overexistence, or rather the saturation of carbohydrates sometimes can cause, it contributes to the muscle pulls that people have sometimes. Yeah, so this is the whole idea that they're trying to put across when they say glycogen storage diseases. Yeah, so people have frequent muscle pulls, so could be they're not watching their diet in terms of the carbs that they take. So, okay, that's just for your own information. Now, back to what we're interested in. So you just want to learn this and pass, right? That's what we want to do. So now here are the classification of carbohydrates. We have 4 major classes of carbohydrates. The first one is simply monosaccharides. So these names, the saccharide just means sweet. That's the Latin word where this guy came from. So saccharide just means sweet or sugar. Yeah, and the prefixes in front simply signifies the number of monomers that we are having in a particular structure. So when they say monosaccharide, these are the simplest type of sugars, meaning there's just one sugar that is contained, right? None of these are called simple sugars. Disaccharides, meaning you have 2 monosaccharide units combined. They form what? They form a disaccharide. Then oligosaccharides, you have 3 to 10, a chain of 3 to 10 continuous monomers, or rather monosaccharides. They produce these oligosaccharides. Then if you're looking at a polysaccharide, meaning when you have 10 or more units of what? Of monosaccharides joined together. Sometimes we'll talk about this. Sometimes they are joined via what you call the hydrolysis process, or dehydration process. Yeah, and this sometimes can always produce something that is very big or enormous, which is going to be talked about in terms of how the structures are going to be formed. How are we able to have such big molecules in our systems, right? This is because these guys are compressible and so on and so forth. But these are just the 4 classes that you need to know. And we'll start by discussing each one of them one by one. So let's start with monosaccharides. And you are here you are informed that provided the monomers, or rather the monosaccharides, are identical, we call that type of polysaccharides to be a homopolysaccharide. Homo just means uniform. Then heteropolysaccharide just means different. Yeah, so this is when the monomers, the units, the subunits that are joined together, if they're all uniform, never same. If you join maglucose cheka, meaning that is going to be a homopolysaccharide. But if you join, let's say, glucose, sucrose, so if the monomers, what you are joining are a lot and they're different, we can always call what we get, instead of just saying polysaccharide, we can classify it further and say it's a heteropolysaccharide. So that's what we basically mean. Yeah, so now we come back to our Unza notes. If we come back to these guys here, we are saying all the empirical formulas for carbohydrates is going to be the same. What will be changing is just the N that will be given outside. Like I gave us previously on the previous page, I gave you something that looks like this. What will be changing the names, or rather the structures, is simply how many carbon atoms that you have, or what's the value of your N. And the proportions of hydrogen, you'll notice here, it always looks like it's a water, right? So it's a water molecule. So no wonder here they shortened it and just said the carbon atoms represented by a subscript X and water molecules represented by a subscript Y, because oxygen and hydrogen are always going to be in a ratio of 2 to 1 all the time. But I generalized this. I earlier on said all these atoms here, carbon, hydrogen, and oxygen, they are always going to be in a ratio of 1 to 1. So this is always a ratio that you're going to be to be dealing with. Carbohydrates are either aldehydes, so I want you to take this serious, aldehydes or aldoses, or ketones or ketoses. So I'll be using ketone and aldehyde in this particular video to differentiate these guys. And they all contain several hydroxyl group. And what we just mean by aldehyde and ketone, I'll just take a step here and just explain what this means. So if you have, rather we say, all carbohydrates have what you call a carbonyl group. So a carbonyl group is just the existence of a carbon to oxygen double bond, and this can be anywhere, but then the only thing that we can have is carbon connected to the chain. So what I mean is, if you have a long carbon chain like this, let's say you have something like that, this is what we call a carbonyl group. So if this carbonyl group is located at the terminal meaning at the end, and this side here you see what? You see a hydrogen. This is going to be called aldehyde. So this is going to be called an aldehyde because the carbonyl group is squeezed in between a carbon and a hydrogen, and then it's found at the terminal, right? That's the only time we call a particular sugar to be an aldose, or rather an aldehyde. So we can either be using any of these two terms. Then if you have the carbonyl group, this here is a carbonyl group. This is what we call your carbonyl group when you have carbon to oxygen double bond. If the carbonyl group, the C or that, is franked or rather squeezed between two carbons, so there's a carbon here and there's a carbon here, this here is what you call a ketone. So this is a ketone sugar, or rather we call it what? A ketose sugar. So that's basically how we're going to be differentiating this. So in as much as we are saying there are 4 classes, but those 4 classes sometimes can have these structural differences. So the structural differences just depend on the location of the carbonyl group. That's what we're basically trying to put across. And most of, if not all, they have a good number of hydroxyl group, and you see the reason why. This to some extent makes carbohydrates to be soluble in water to some certain extent. And here we're saying aldoses or aldehydes with a terminal carbonyl group are more easily oxidized than ketoses with a non-terminal carbonyl group. So no wonder we call aldehydes to be reducing agents. So remember that experiment you are doing in high school when you say you are testing for reducing sugars and non-reducing sugars. So those guys you were saying they're reducing sugars, those are simply aldehyde sugars. Then the ones that you were saying to be non-reducing sugars were ketones or ketoses. So that's basically what we're having. And we can dive in to discuss the first class, which are carbohydrates, known as monosaccharides. So these are the simplest form of carbohydrates you ever find. They're only made up of a single monomer or a single sugar unit. These are mostly used up by cells as a direct source of energy. We cannot store these because they are in their simplest form. They are always ready to be used. So other forms like disaccharides and polysaccharides can be taken to be forms of energy storage, forms of energy in terms of the sugar that we consume. So when you consume some diet that has carbohydrates, there is only a certain portion of that food that is going to be used by the body there and then. Most of it is going to be conserved, and when it's conserved in a bigger structure, so that it's always going to require a certain period of time for us to break down that sugar whenever we need it. Yeah, so here that's the point we're trying to emphasize, to say monosaccharides are a direct source of energy. They are not used as storage forms, but they are used as direct source of energies. These are classified according to the number of carbon atoms that they have. We have classes as well here. So you can have what you call trioses, we can have what you call tetrasoses, or pentoses, or hexose, or heptoses. So it's like tri, that's 3, right? Then tetros or tetra, that's simply 4. Pentos, sugars. So the os at the end is because that's the prefix that we'll be using mostly, and this is because these are mostly going to be aldehydes type of sugars, and we're simply saying they can either exist in terms of in terms of an open type of structure, or it will be a closed or a ring form of structure. Yeah, so the open chains can exist as different isomers of a given monosaccharide. So hope you know what an isomer is. So isomers are simply molecules with a different structural representation but the same molecular formula, right? That's what you define an isomer to be. So we can always have these two forms, and the common ones that you study. So we cannot exhaust all of them. So there are a lot. The same thing like you had in organic chem. You remember what you used to say? You have what? You have pent, hexa. You have those. If you are naming those groups that you had in organic chem. So it's the same thing even here. The only difference is that, remember we said N only starts when it's greater than or equal to what? 3. No wonder we're starting on trioses, right? And the common ones that we'll discuss are these 3, because their names are familiar in the food or in the domestic food that we mostly consume. And we're saying the most common isomer is the D isomer, or the optical isomer, which rotates whenever exposed to what? Polarized light. So the D isomer just means dextro. The L isomer is rare and rotates polarized light to the left. This is the L just representing, or rather the initial for levo. So maybe to show you what we are discussing, this is what we are saying here. We have so many examples of monosaccharides, and the common ones that we're going to be dealing with are the ones that are trioses, pentoses, and hexoses. The ones that have 5 carbons, 3 carbons, and 6 carbons. These are the common ones. So here is a typical example of D-ribose and L-ribose. So you see that D-ribose is simply the mirror image of L-ribose, this side. So the D and L is because of how it's structured. So take D to be the dextro one to be like your left hand side, and take the other guy to be like your right hand side. Now there's a mirror in between, so sort of you can think about it like that. So when you rotate this guy, you get this other part here. And I should be clear here that we're just rotating the middle part. If you notice, we don't rotate everything, only this part is being rotated. That's what you notice. The terminals are still unchanged. This is what you get. The same applies if you have what? D-glucose and L-glucose. This middle part is untampered with. We only rotate, the terminals are untampered with. These are still the same. We just rotate these ends. This is what we just experience in terms of having polarized light exposed to these molecules that we'll be discussing. Yeah, so this is just explaining this type of structural isomers that you'll be seeing. And the first type of monosaccharide that we dive in are trioses. These are only monosaccharides with a continuous carbon chain which has a number of 3. And the typical illustration that they give us here is this guy here. They're saying there are 2 biologically important trioses, sugars. There is glyceraldehyde, which has 2 optical isomers. There is L, and then there is D, glyceraldehyde. And then there is dihydroxyacetone, a ketone or a ketotriose with its carbonyl group located at the center of the chain. So these are the most common, these 2 guys here, these are the common trioses that you need to know. So there is glyceraldehyde, and we're saying this can either exist as L or D. And D, we simply say this is what you have. So we can call this guy D, and then we can create our L. You know, to say when you create L, nothing changes. This will just be something like this. The middle part is the only part that changes. The terminals will still be the same. So this will be, okay, so this is simply going to look like this. So you have your D-glyceraldehyde, and we have our L this side. You notice the only portion that I've changed is just this. This is the effect of polarized light. So by polarized light, we just mean a typical light media that has both positive and negative charges. Yeah, so it keeps the terminals constant, or rather held in their positions, and just shifts the middle part. So the same would apply for the dihydroxyacetone. You can just switch this middle part. You can create your D and your L isomers. So that's what you have in terms of triacetes. So if you notice the name here, I've made it short and just said glycerolaldose. It's the same thing as finishing it off and saying glyceraldehyde. So the prefix or shortcut of aldehyde is just aldose. Yeah, so you notice the difference in how some authors are going to be writing their aldehyde sugars. And here now we're saying, aside from the 3 carbon monosaccharides, sometimes we can have 5 carbon type of sugars. So meaning our N is 5, the same empirical formula that you had, which was this, we're now just saying we're multiplying by that. This is 5, this is going to be 10, then this is going to be 5. So this is where this is coming from. Now the usual or the common ones are ribose or ribose and deoxyribose. So from these 3, the famous ones that you'll be looking at mostly are the deoxyribose and the ribose. So the ribose has more oxygens or hydroxyl group as compared to the deoxyribose. This guy is deoxygenated. Yeah, so ribose is an important carbon dioxide acceptor during photosynthesis, while ribose and deoxyribose are important components of nucleic acids. So ribose is one of the components that you find in the structure of green plants. Most plants that require photosynthesis, which is all if we just do it, generalize it, so to say. Yeah, so this is part of the point we had mentioned earlier on, to say sometimes carbohydrates can be found in the structural support part of either animals or plants, but this is specifically in plants. Yeah, and we are going to focus on the application, or rather the existence, of ribose and deoxyribose, because they affect us in the way that they support the components of nucleic acids. Nucleic acids, this is very important to us humans, because this is going to help us discuss how our genetic information is transferred, or rather kept for a longer period of time, generations to generations, how we preserve our DNA and all these other things that we'll discuss about. So here we're just going to dwell on the 5 carbon sugars, giving structural examples as follows. So this is ribose and deoxyribose. You can just, so the ribose is going to be found in RNA, then the deoxyribose is going to be found in what? In DNA. Yeah, so ribose is a constituent of RNA, while deoxyribose is found in that. When a 2 carbon blah 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 here. So this is just can be seen from the structural difference that you see here. So look at the ribose sugar. So the ribose sugar has the carbonyl group at the terminal. You are seeing the carbonyl group here. Whenever you see a carbon to oxygen double bond, just know this guy is what? This guy in particular, this portion is the what? That's what we call the carbonyl. So now the carbonyl is squeezed between a hydrogen and this long chain. So this is an aldehyde. The same applies with this part, which is the deoxyribose. Now they are all D structures or D isomers. So we don't have to always draw the L structures. We know we can create them by just rotating this middle part, right? We can create L deoxyribose. The same applies to this, the LIVO isomers. So if you notice the difference between these guys, can you tell the difference between these structures? Okay, so if you check, the difference between these 2 structures is that the ribose has an extra, has a hydroxyl in place of a hydrogen. So this is the only noticeable difference between these 2 sugars. They're all 5 carbon ringed type of structures. They can be formed in a ring form, which is the usual case. But what only differentiates them is that this guy is more oxygenated as compared to this other guy. Yeah, so this is known as deox, like deoxygenated deoxyribose, meaning the removal of 1 oxygen from the ribose creates what? Creates deoxyribose. So this is basically what we are having, but everything else is still in place and everything else is still the same. And this same striking difference in terms of the number of carbon atoms is going to simply create what we call the alpha and the beta structures. So if you look at your D-ribose structure, this is what we are having. If you were to disconnect the fourth carbon, so we are counting first from the carbonyl group, we count the carbonyl group to be the first carbon, going down, so we are saying, look at the arrow here, we are connecting the fourth carbon is having an oxygen here, right? So we're trying to connect the oxygen on the fourth carbon with the first carbon. That's what we're trying to do, right? So if you open up the bond, so maybe I may show this, let me just show this. Okay, so to simplify the whole representation that we're having here, we're saying a straight line D-ribose pentose sugar can be transformed into a ring structure, and that can only happen in such a way that we're going to link the oxygen on the fourth carbon with the first carbon. That's what we're basically saying. And after we are done linking these two, connecting them, the oxygen that was on the first carbon is going to form a hydroxyl group with the hydrogen that was on the fourth carbon, with which was bonding to the oxygen. So now that you see the maintenance of the colors that you are able to see on the ring diagram. And whenever the hydroxyl on the first carbon is above, we call that to be a beta ribose structure. And this actual name should be actually be your beta D ribose. So this is supposed to be ribofuranose. So furanose. So this is the name that is given to this ring D structure. Yeah, so this was just supposed to be D ribose initially, then it's now converted into a ring structure form. Yeah, so we can change this and call it alpha if we just interchange the position of the hydroxyl group. So if I change and put this hydroxyl group down, the hydroxyl group that was there, and put hydrogen, this now changes and becomes alpha. So this will just change and now become what? Becomes alpha. This is what you'll get. So this is what they're trying to illustrate here, to say straight line expressions, or rather molecules, can sometimes be converted into these ring-like structures, and this is what you have. Yeah, so you can either have the beta one or you can have the what? The alpha one. It just depends on the location of this hydroxyl group. Yeah, so if it's below, that's alpha. Yeah, and then when it's above, then we call it to be a beta type of structure. Now there are so many pentose sugars that you're going to look at. Now these were ribose illustrations. Now how about a deoxyribose? And like you noticed previously, we said the main difference between a ribose structure and a deoxyribose is that they may contain the same number of carbon atoms, but the deoxyribose is lacking, or rather missing, this hydrogen that the ribose had. You see this difference, right? So that's the main noticeable difference between the ribose and deoxyribose. The same steps are going to be followed to produce a ring structure, and also you can also have a beta deoxyribofuranose, or you can have an alpha D deoxyribofuranose, depending on the position of your hydroxyl group. Yeah, so this is what we basically have, and these are all just covalent bonds. No wonder we are seeing that the changing from a straight line structure to a ring structure does not change the saturation, or rather the number of bonds that you're going to see. Later on, you're going to have to learn what we call the pi bonds and the sigma bonds. So we can always check to find out that the number of molecules, or rather the atoms, have been preserved. Nothing has been lost. We're just changing the representation. That's basically what we have. And in most cases, we would prefer the straight line structures because these are a bit reactive as compared to the ring structure. In the ring structure, you notice there is no double bond here because of how we arrange the atoms. But in a structure that we can see a double bond is very reactive as compared to single bond. So this is always in a reactive form. This is mostly what you see when it comes to monosaccharides. No wonder most of them are just in a straight line, because these are direct source of energy, giving what? Carbohydrates. But for bigger structures, we'll prefer putting them in ring form because those are energy storage type of carbohydrates. So that is what you should also take note. Now, how about hexose sugars? Hexose, meaning we now have what? 6 carbons, right? That's where the hexose is coming from. So we have 6 carbon sugars. Yeah, and a typical illustration from our same empirical formula, we multiply by 6. This is what you get. Common examples that here we'll talk about in details are glucose, fructose, and galactose. That's what you have. They are direct source of energy and are oxidized during cellular respiration. Glucose in particular is the most common one. So this is the most common respiratory monosaccharide. And hexose are used in the synthesis of disaccharides. So when you combine 2 monosaccharides, in particular hexose sugars, you will form disaccharides. Of course, there are other monosaccharides, but we're saying the common ones that we are going to be referring to, or rather the common ones that we'll be using to create disaccharides are mostly what? Are mostly hexose sugars, because these are very important, and you did learn this somewhere in high school. You did learn the combination of what these guys give us. For instance, if you talk about what? If you talk about the whole carbohydrate, let's say we talk about we say what? We can say lactose, for instance. There was this, if I remember very well. You can say lactose is simply the same thing as what? You can say galactose. When you combine galactose plus glucose, this will give you what? Lactose. So these are monosaccharides. You combine 2 of them, you produce a what? A disaccharide. So this is why we are mostly going to focus on these, because not only do we hear them often, or rather do you read about them on the food stuff that we consume, but because they are mostly preferred whenever we need to create something bigger. So whenever we want to start building up, we always prefer using these guys. Yeah, so let's dive in and discuss them in detail. So we want to talk about glucose because we always need this guy because of the cellular respiration. We need it as a source of energy. So what do we know about glucose? So glucose is simply a grape sugar. It's a monosaccharide that's found in plants. It is important. It is an important product that is it's a byproduct of photosynthesis and is a fuel for cellular respiration. So this guy, you know the formula. The formula is very easy. 6. So the formula for all 6 carbon monosaccharides are all going to be like this. This is the actual formula, the molecular formula of glucose. This is what you have. This is your glucose. Now we say this guy is soluble in water, mainly because of the intense hydroxyl groups that it has. Hydroxyl groups which form hydrogen bonds with water. The open chain of glucose is an aldehyde whose carbon 1 combines with the hydroxyl group from carbon number 5 to form a 6-membered paranose ring. So you really don't have to know these all the furanose names and the paranoids. You just have to take note of whether your structure is now going to be an alpha or a beta glucose, depending on the location of the hydroxyl group. Yeah, so to cut this all short, I'll take you straight to the straight line structure of glucose. And we're saying glucose is an aldehyde sugar. Why? Because it has the carbonyl group at the terminal, and the carbonyl group is directly linked to a hydrogen. And if you want to change this guy into a ringed structure, we're going to combine. This is carbon number 1, by the way. This is 2, this is 3, this is 4, this is 5, this is 6. So we'll get the oxygen on the on the 5th carbon. So we can do this in 2 ways. It's either you get the oxygen on the 5th carbon, this guy here, and combine it with this carbon from the 1st carbon, from the location number 1. So when we join these guys, this is what you see. So this is what you see right here. This is what you're having. This is carbon number 1, this is carbon number 2, number 3, number 4, then number 5, then we had number 6, because we got this and connected it there. I don't know really why they always use the arrow in front, because to easily see this nicely, I would prefer we say this carbon is, it's like bent, it's like they bend the cellular structure, then tabatacha connect kumbuyo. So that you see that it's going to be 1, 2, the arrangement, why we're writing 1, 2, 3, then 4 and 5, then a 6. So it's literally us bending it from the other side. Yeah, I would prefer us saying we are opening this guy. This is a double bond. What I mean by opening is we are opening this. So this double bond, I can close it there and just open it there. So 1 will still remain intact there. Then 1 remains loose this side. Then I connect this guy with this carbon. Now I have to remove this hydrogen, which was up, and put it together with this other carbon. So this is what you're going to have. You can literally say that. You can have something like that. Yeah, so however you understand it, all we are saying is that the D-glucose can be changed into either being an alpha. You won't produce both of them. Yeah, so here we should have been writing O, not plus. We can either produce the alpha glucopyranose, or we can produce the beta one, depending on the location of the hydroxide group that you have. Yeah, so this is the most important hexose sugar that we're going to be discussing, because we need it and we use it often in our cellular respiration, which is an energy giving process, so to say, to us humans, or mostly mammals. It's a byproduct with reference to plants, but to us, it's something that we need on the reactant side to produce energy and so on and so forth. So same applies with galactose. The properties are almost similar, and they should be similar because the structures are still the same, because it's still a hexose sugar. So even this guy also has 6 carbon atoms, 12 hydrogen and 6 oxygen atoms. The only difference is in the structure. So remember we said what? We said glucose is an aldehyde sugar, right? Aldose. Same applies with this. The only difference is you see how these guys are arranged here, right? If you go back to the one for glucose, so glucose, if I may just write it here so that you see the difference. Glucose was the carbonyl group, this guy with hydrogen. Then this guy here has a carbon. So let me just pick this space. Okay, so hope you'll be able to see it here. We have carbon there, then we have hydrogen. Then here we are just having a carbon. Then you have this guy. This is hydrogen. Then this is carbon. Then this is hydrogen there. Then this side you're having this part. Then look at what you have next. What you have next is hydrogen. Then this side you have a hydroxyl group. Then you have the next one, which is just a carbon and a hydroxyl group. Then there's a hydrogen. Then the last one you have the C2OH. So this is how our glucose structure was. But look at the galactose. Galactose has concurrent hydroxyl group on the 3rd carbon and on the 4th carbon. Whereas here on glucose, these guys are alternating on the 3rd carbon and on the 4th carbon. You are seeing what we are having here, right? That's the main difference between glucose and galactose. This same location of the hydroxide bonds give these guys their minimal but significant differences. So this is basically why they might be both hexose sugars, but they have different names and different properties and usages because of how the structures are. So this is what you are going to get or make out of the straight line structure of a galactose molecule. You can either also have an alpha one if the hydroxyl group is down, or you can have a beta one. So here again we should have said O, because you can only get one at a time. Yeah, so it depends with what you are getting. Then fructose is also a hexose sugar. It's mostly found in fruits and it's soluble in water. Common things that you can find fructose is in honey, in flowers, in berries, and in root crops. Yeah, like sweet potatoes. Yeah, so those are typical cassava. Those are typical example of root crops. The open chain of fructose is a ketone. So this is a ketone because of the location of the, so here I want you to see this. This is a fructose thing, and we're saying it's a ketose. We should emphasize here to say this is a ketose. Why are we saying it's a ketose? Because the carbonyl group is squeezed between a carbon and a carbon. There's no hydrogen related to the carbonyl group. Yeah, that's the main reason why we're calling this to be from the ketose group. And these are the two structures that you can get. You can either have an alpha and a beta stew, basing it on the location of the hydroxide group. That's what we focus on. So the same way we made the other two ring structures, it's the same thing, though here we're attacking from behind explicitly because the carbon that we're using, which is from this part, we're using the hydroxyl. In short, we are combining. So from here we're just saying, just combining your carbon 2 and your carbon 5. Yeah, so this is basically what we have. So it will create this. Then aside from these structures, we have these technical things you need to know in terms of the type or the different isomers that we can have. So we said isomers are simply different representations of the same thing that have the same formula. So optical isomers, this is what we are calling the D and the L. Those are typical guys that we call what? Optical isomers. Then stereoisomers, these are simply molecules which have the same molecular formula and structural formula, but differ in the spatial arrangement of atoms in terms of the alpha and the beta. So those are called stereoisomers. And the best way you can know the number of stereoisomers, we use this formula here, is equal to 2 to the power n. So this is the number of the stereoisomers you can possibly get, where n simply denotes the number of stereogenic atoms in a molecule, or rather we just mean how many central atoms are you able to see or locate in a particular molecule. So central atom, we just mean an atom that you can either rotate the whole thing, the whole structure that you have, it can rotate, or rather where the structure is symmetric. So the typical illustration is what you are doing when you are getting the alpha D glucose and the beta D glucose. So those are typical illustrations that you can give in terms of what stereoisomerism mean. So it's the same thing. So now I was putting an O in between instead of a plus. So those are just isomers, stereoisomers. The rotation, or rather the flexibility of the molecules with reference to the hydroxyl group. So we're saying, okay, just rotate this back and forth. So that's what we mean by stereo. In other words, we can say stereoisomers. Stereoisomers here, if you want to calculate the number of stereoisomers, here we're saying central, some people say chiral atoms. So chiral atoms are just, in this case, the carbon atoms that are bonding to different things. So if you look at this guy here, let me say this guy here, so completely different things. So carbon number 1, is it a stereo or a central atom? So this guy here is not, or rather let me take it from this guy here. So you notice there's a carbon here, right? This carbon is not a central carbon because it's bonding to a carbon and then another carbon. So it's not. This carbon here is bonding to a carbon and then another carbon. So this carbon here is the only guy that is unique. So this carbon here has, so this guy here has how many things that it's bonding to? It's bonding to a hydroxyl group. There's a hydroxyl here. There's this guy here. And then there's an oxygen. There's a carbon. So they're all 4 different things. So that's number 1. Then which other thing is bonding to 4 different things? Can we discuss this carbon here? Yes, this carbon here is bonding to a hydrogen. Is bonding to oxygen. Then we can say what? We can say oxygen and 2 hydrogens. Then it's bonding to what? What other thing can we put here? So we can put this, actually we can make it like this. We can say instead of water, that will be cumbersome to say, we can say there's a hydroxide. There's a hydroxide group. Yeah, so there's a hydroxide group. If you try to make it now, there will be a hydrogen there and then connected to this other carbon here. So you are seeing there are two hydrogens. So this is not a central atom. The only central atom here is this guy here, right? This guy. So this is 1. So in other words, saying 2 to the power 1, this will just give us what? 2. So that's the main reason why for hexose sugars, which only contain 1 central or chiral atom, can only have what? Can only have 2 stereoisomers, which is the alpha and the beta one. So that's basically what we have. And this can also be concluded by just looking at this last part. The other type of isomer that you can have are known as structural isomers, molecules which have the same molecular formula but different structural formula. It's just discussing something like an aldehyde and a ketone. So take for example, I showed you how the glucose structure is and how the galactose, even that we can compare the two, but that will be a bit hard for you to see because they are both aldehydes, right? But how about between a ketone and an aldehyde? So because you know the structure of fructose is a ketone, so what we just mean by structural isomers, you just shift something in the fructose molecule. Look at the position of the carbonyl group. So it's on carbon number 2. In the glucose, in an aldose sugar, the carbonyl was on carbon number 1. So this is what we mean by structural isomer, because we just change the location of the carbonyl group, but the molecular formula is still the same. They're all going to have the same C6H12 or 6 what type of molecular formula. If you calculate their molar mass, it's still going to be the same. So that's basically what we can say in terms of monosaccharides. So this brings us to the end of this video. This is just in particular to introduce carbohydrates. The next part that we're going to look at is the other class of isomers, which is simply disaccharides. That's what we're going to look at next. Yeah, so we'll try to combine disaccharides and the rest so that we just have 2 particular videos. So thank you so much for watching. If you do have any questions, feel free to WhatsApp me on 0978 73 90 38. Yeah, so in case you have anything contradicting what I had mentioned, you can just feel free until we reason together so that at least we have the correct information about monosaccharides. So thank you so much. See you in the next video.